Yeah.
Like, yeah, that's it.
Yeah. like genuinely, if you just like go to this too, you just click this, there's just, like, it's just right there.
Yeah. This is definitely one to cheat sheet.
50 goes really. Very specific.
I have like some back-end stuff. Let me ask one of those. You really put them on the same place.
Give it another 2-3 minutes for people to come by, and then we'll get started. How did I petition it? I forgot. How are we gonna petition it? Yeah. Who does what? I remember talking about it.
Yeah, you sent me a message. Oh fuck.
Wait, it made sense when I sent it. I literally forgot what I said.
He said half every step 45. So half every but then that's
okay, so I could start. Part 1 is like a chunk of 45. Remember the part 0.
really more content just because I'm not practiced using it. But
yeah, because then it just like demos like sort of the things that you would kind of command you use, and just like I guess what I look like with that, and then just like I just did part 0 and everything after 45. All right. Hello, everyone. Welcome back to CS50. This is section number 7. So this week, we're going to get started with SQL, transitioning from everything that we've worked with in Python and sort of working more on like the abstract database that we're going to use in this course. And so SQL is one of those languages that we introduce in CS50. It probably would come very handy in your final projects as well if you choose to store information in whatever way and you were like, I would like to have an SQL database file just so that I can keep track of all these forms, all these information. But before we get there, let's dive in and figure out what SQL is. So to start, we're just going to go over the abstract idea of SQL. So SQL is a language that essentially works a lot with databases. If you recall in C, we worked with storing information in memory, and then we were like learning how to like iterate through in a very like low level. In Python, a lot of it kind of just gets done for you, and you just if your theory is correct, then Python just like fills in the blank and try to like assist you in doing that. SQL is somewhat similar to like the syntax of Python, in which the code can be translated directly into like how you would say what you want to do with the information, how you want to set up things. But it's just designed in a way to keep your information organized and making sure like these databases are there to give you all the info you would need in a pretty efficient way. So before we get anything like too deep into SQL, let's just think about storing information. So suppose this is you. You can be any of these three. In fact, you could be some shadow in the background. Doesn't matter. But that is you. And you have some sort of information that someone wants to know. And so me as like a reporter come up and I'd be like, hey, can I ask you this question for a survey? Blah, blah, blah. You give me your answer. I keep it in some sort of storage. And then after I have the storage, I can then analyze it. I can put it into a graph. I can do some research in it and then publish it in some way. So where SQL comes in is essentially wherever you use your databases before you try to figure out what sort of trends happen, what sort of connections there are between all of these different pieces of information. Because like if you're just given a really large transcript of something, it's pretty hard to find patterns, especially if it's like all writing as well and like not numerically comparing, stuff like that. So SQL essentially is the storage piece. It's the database piece of your processing of information. And so given that SQL is like something that's designed to be a database, it's designed to keep track of information. In an abstract level, doesn't have to do anything with any details of the code. What do you think are some priorities? What are some design choices that impacts the people behind the data, those who are consuming it, those who are collecting it? What are some priorities that you would want to have for something like this database system to work well? What are some things that you would want to optimize when you have such a language? Talk to the people around you, and then we'll come back in like a few moments.
I guess you'd want like quick access. You want to be able to sort through the data as quickly as possible. No mistakes.
And then also, there's no right or wrong answers. We're just trying to gauge just like an intuition onto what is actually important when it comes to these languages. So very abstractly, what are some things that we care about when we want to create a database or like use a database system? What do we expect it to provide for us? I don't know, like anything.
You want to be secure.
You want to be secure, so you don't want someone to like accidentally like walk in and like start deleting everything. You need people with certain access to only be able to read and write stuff. Awesome. What else? Maybe one or two more things. Yep.
You want to be able to sort through the database as quickly as possible.
Sort through them efficiently and as quickly as possible. Awesome. Yeah, keeping track of the data in a way that is that you can understand, and then also easy to manipulate to figure out where things are, and that's usually done through sorting. Awesome. Anything else? One more thing, maybe.
Something where like the data can be changed.
Yes, the data can be changed. You don't want a database where you just insert something and then not be able to modify it, and the only way to modify it is just like rip out a chunk of it that's like unusable, and then it just gets inefficient. Awesome. Yeah, so making it dynamic so that you can change items. Awesome. Yeah, so these are all really great intuition when it comes to designing a database. And we'll actually touch upon all of those aspects as we discover how SQL works. All right. So just for general notes, the way SQL works is, so you have this language, right? In an abstract level, you're creating a table somewhere where there's like a category, bunch of information, next category, bunch of information. You can have multiple tables together. You can have a table with many columns. You can have a table of just 2 columns, things like that. For design purposes, to keep things organized, in SQL, each table should be a collection of a single entity. So what does that actually mean? For example, let's say you have a database called students. And inside there are 3 separate tables. One table that says courses, one table that says people, and one table that says students. So all of these are like related to each other, but they are in separate tables. They all help convey a message. Like you can look at this and be able to tell a story, but each piece of information should be isolated such that you can easily manipulate it in conjunction with each other. You don't want one and only one table with everything in it. That way you have to load everything all the time. If you only want a very certain piece of information, you don't have to load the entire file. Things like that. So for design purposes, you try to separate things into like very specific categories. You can also see that some of these repeat across the tables, which then we'll also learn how to piece them together, join them together, select things across tables in order to use the entire database. So database could be composed of multiple tables. And one more thing is that each piece of data should be stored in a single location, very similar to what we were talking about, sorting and keeping things efficient. You don't want the same piece of information to exist in multiple places that don't serve any new purpose. The fact that a piece of information can exist in multiple places could happen in SQL, but each of those instances has a reason on why they're there. You have to avoid the case in which you're repeating information for no new apparent reason. That way, it like just very like intuitively, it just like clogs up your data. It makes it difficult to sort. It makes that the duplicates like falsify some of your data, which is something we don't want. So try to make sure that you are aware of like all the categories that are in your schema. Schema is something that we'll talk about in a moment, but they're just like general design purposes and just abstract level of thinking about SQL. Similar to how like 2 weeks ago we were talking about like hash tables and hash functions, and there are like criteria on how to write effective ones. These are also things that to keep in mind for SQL for databases. So going from here to now here, the core thing that changed is the introduction of these IDs across the tables. Each of the table have like their own sets of IDs. That's just how you keep track of the entries across your table. And another thing is that all of the categories are in lowercase. That's just like convention. You don't have to follow it, but it's just easier to keep track of categories that way so that you don't mess up like thinking econ 10A is a category when like it's just like class code or semester. It's just the cases of writing names essentially in SQL. They all have a reason. Yeah, so if you were to like look at this database right now, each of these mini tables inside the database holds a different piece of information. Without knowing anything about this and assuming that the ID is consistent across them, you might be able to piece out each of the line relating to each of the students, perhaps. But each table carries a different piece of information. Nothing gets repeated across them unless it's something like ID that helps you identify and piece information together, which we'll talk about. So that's just to explain this second point, that the information should not be repeated if there's no new reason to do so. So that's very abstract level of thinking about how SQL works. We're now going to look at more specific commands and then details of how to operate, create tables, insert, delete, and all that. So,
Hey everybody, I'm gonna be really honest with you. I'm walking you through the commands because I'm not super good at SQL, but this is going to be a really good way for us to just like really quickly like see the different sort of like high level things from the language. So we're not actually going to use them until sort of later in the section. But so first off, you want to be able to create a database. And what you're going to do is you're going to run a program called SQLite3. Now, when you are using a database, just any type of database, what that actually is, it's a program that you're going to kind of interact with. And you're going to say like, hey, can you please like give me some information from my database? Like, you know, you're going to be kind of talking to it to get information from it. Students.db is the file that actually contains like the information itself that you're trying to store. And SQLite3 kind of interacts with this file, and then you kind of talk to SQLite. So in your terminal, this is how you would make this database, students.db. So that kind of makes your database. Now you actually need to make a table, right? And you can think of this, you know, like Kang did a really good job showing the tables. It's kind of like making like a tab in Excel. If you're familiar with like Excel, you have like multiple tabs. That's kind of what these are like. And what you're going to do is you're going to define some information about the tables, the table, especially if we're talking about things where we've kind of organized it in terms of columns, right? So you have like the name of the column, the type of data that you want to put in the column, and then some specifiers, some specific things that we want to kind of like rules for the data that should be in the columns. So you use create table. You can use create table to make a table named courses that has two columns, for example, ID and code. And then, yeah, you can just put any additional attribute there. I want to draw your attention to this thing called this ID here and this primary key thing. So what primary key means is it's sort of a promise that you're making, and also SQL is going to kind of yell at you, is you're saying that basically ID, each row, each ID is going to be unique. Kind of the reason why that's the case is because it gets really, really messy if, for example, you might have two rows that have the same ID. Could you imagine if, like, at Harvard University, right, you have your own student ID and somebody else had that exact same student ID? That would be a mess. And so a primary key is a very important part of kind of keeping organized. It's sort of an assumption that we're going to make about our rows. And so we're basically saying this column, ID, is going to be unique for each like entry. So if you wanted to make this table, create table courses, we're defining the IDs and the code. So these are like ID, code, semester. These are the columns. And we're saying that the primary key, the thing that's going to be unique to the course, is the ID. So each course, like at Harvard, in the course catalog, has its own unique ID. Because again, it would be really confusing if you sign up for one course and it's actually a different one because two of them share the same ID. Whereas they could kind of share the same semester and like their name could be sort of similar. Now, an important thing might be the type of data that we want to represent here. So the ID, it makes really a lot of sense for it to be an integer. The code could be like, CS50 that has, letters and numbers. That could be a string, a text. And then you could have something like the Q score, right? Or just some other information about that course that you want to be in the row. Some other, some rules that we might have for these are that we do not want any of these entries to be null. Null meaning basically there's no information there, right? Every course in this table should have an ID. It should have a code, it should have a Q score, or else it's like not a valid entry to the table. All of these just really important things for, when our database scales, it makes it a lot easier to work with the database if we can have some very structured, nicely structured rules for the data that can exist there. So let's say we wanted to insert something into our table, sort of like inserting a row. We can use this set of commands here. Insert into our table the following two columns, and we want to insert values corresponding to those two columns here. So you can think of this as sort of like one command. So if we wanted to insert into our courses table a course ID and course name, and then we could set the values for it. Yeah, so you could use insert to add 3 courses into your table, for example. So you could insert the code CS50 and Q score 4.11 into the courses. Kang, do you know if the ID will be automatically generated if you do this, or if you need to put the ID in yourself?
The ID per table, like
yes, the primary key.
Yeah. If you specify something as primary key, it keeps track of it.
Okay.
This essentially gives you like the 2 coordinate thing to like
Yeah.
be in the right spots, so it should be already.
But I'm just wondering if you insert into this, would it be fine without you specifying a primary key? Okay, so it'll just assign a new primary key to it. Like it'll get a new ID. Okay, important. Okay, so yeah, even though we did not specify the ID, the database itself will make a new ID for this entry into the table. Another thing you might want to do is update the entries in the table. And so for that, you can use this set of commands. All of these, by the way, are in sort of the lecture notes for the most recent lecture on the CS50 website. So you might want to use that as a really good reference, just to kind of like, if you want to do something in SQL, that is a good reference for that. So for example, we could update our course Econ 10A to change its like course offering from the spring to the fall semester. And so we could update our courses table, and we're going to set the code. We're gonna find where the code is equal to Econ 10B, we're gonna set the code to be equal to Econ 10B where it's currently equal to Econ 10A, as an example. We can also delete from our table. So we can use delete to remove Econ 10B from the courses table by basically saying delete from our courses table the entry where the code matching that entry is Econ 10B. Okay? So next we might want to sort of get a bunch of entries with stuff in common. Like say you're searching on like the Harvard course catalog and you're trying to look for like all of the courses that are being offered next semester that are above like a 200 level, right? You might kind of use this type of command in the back end of that website to do some of that searching. So yeah, we can select the columns from the values of the columns from the table where some condition is met. Yeah. Okay. So yeah, as an example, we have a songs database with sort of each song having an ID, and then our columns being the name, tempo, the duration of the song, say like in seconds, and then an artist ID. Then we have our artist table that has sort of these IDs and then some information about the artists. So one thing you'll notice about SQL, this is a very old type of database, and it's not actually the best for every single use case. Notice that if you want to figure out the artist of a song, you have to like go look at the songs table, find the artist ID, and then go to the artist table and then find it from there, right? And like the information about it. So you have kind of like separate tables that are each kind of storing their own thing. You can think of it similarly to if you make two different arrays where the index sort of means the same piece of information, like they're connected like that, but you just have two arrays instead of something like a struct like we've used before to organize our like information together. Yeah, this is just one type of database and sort of how that works.
Okay.
All right. So with like those initial like commands in mind, there are some like modifying things, some editing things that you could do once like you've had your tables established. So we've separated into these 4 categories here. We have selecting, ordering, limiting, and aggregating. So starting with selecting, here we have this example. Select name from songs where the duration is less than 240. So if you look at this, we're going to see, we're picking some items from the name column from the songs table where its duration is less than 240. So you're interacting with like different components here. Name and duration are items within this table. And then songs could be like the name of the table. And so you're basically specifying which columns, which attributes, and then once those things are matched up, you would then return everything that satisfies the following criteria through the select query. So using this, select name from songs where duration is less than 240. We go back to our example. We're going to go into the songs table. Also, this is a little misleading. There's the songs database and the songs table. When you're running this, you're talking about the songs table. The database itself does not appear in any of these queries. It just happened to also be named songs. So from that again, select name from songs where duration is less than 240. So select name just identifies this row, so it's going to return something in this row. From songs, from this table, where duration is less than 240, so it's going to go through the entire column of duration, finds whatever is less than 240, and then returns the name column of that row. Each of these rows an entry. When you run something like that, only the name gets returned. Okay. If you don't want specifically like any like explicit criteria of something, you could also use the keyword like. And this example happens to be a lot about like the naming. So assume, I don't know, you want the word love to appear in the name of the song. But you can't just say select name from songs where like the name is love. Then it's just going to find whatever song is named love and then return that. And you're going to miss everything that has love in the name, but not as the entire name. So the way that we denote like just containing a piece of information, we can use the keyword like. and then with the help of all of these percents. So if you have this placeholder in the front and then love, that means the name could contain whatever in the front and then end with love. Similarly, love and then percent afterwards, it's going to start with love, anything. And then if you want love just to be in the name, regardless of wherever it is, I have something before, something after, and then love. Notice the other times that we have seen the percent get used in this course is when we were doing modulo, which works with numbers, so not this case, but also placeholders and like also flags for when you were doing print statements all the way back in C. And this is like somewhat similar. It's just essentially acting as a placeholder for whatever is before it, whatever is after, or both of them, meaning that the love is inside. And you can always refer back to these tables to just look at the usage of different commands. So this is the like keyword, and that wraps it up for select. And then moving on to ordering, here we have select star from songs where tempo is greater than 100, order by tempo, DESC. Select star. Okay. We just did select name. You could also select tempo, select whatever. When you do select star, star is a placeholder for everything, essentially. So when you do select star, it's going to return all the attributes that exist within like that row. So like anything about that specific song. So if we're trying to decipher this, it's going to say select all that information of whatever entry from the songs table where the tempo is greater than 100, and then we're going to order whatever we return by the tempo in descending order. What would that look like? Oh, and also, if you don't do like descending there, it would be ascending by default. So there's technically never a need for you to write ascending because it is ascending by default. But just so for sanity purposes, you can include it and then just leave a comment somewhere just so that like we are explicitly clear about how we're ordering things. But it's just descending, ascending, and then you don't only have to do by tempo. If you have like song duration, you could work with that as well. You could have release years, something like that. But these are pretty much about the integers and the floats, anything that you could compare numerically. So that's for ordering. Could also order things alphabetically as well, but we'll talk about that. All right, limiting. As the name suggests, there is a keyword called limit. We've seen all of this before, and here it says limit 1. So if there are, 70 matching entries, it will only return 1, and which is whatever one is at the top. Knowing this, and knowing that you can order by whatever, you could do things like you want the top 5 fastest tempo like ever songs in your database. You could use a combination of both. You could order them by descending and then limit 5. And then it would give you like the top 5 fastest songs from anything that matches the criteria on here. And then just a quick review of like the things that we just talked about. So there's the like keyword in which you can get partial matches of especially like particularly names from this piece set. And then also some examples of that. Select code from courses where code like CS. So this case, which is a nice use case here, all the CS courses are going to be returned because they all start with CS. And so that's a like keyword. Order by, and then you have ascending, descending, but you really would only ever use descending. Otherwise, ascending is just like by default. You can order by your entries and then just let them either be alphabetical in order ascending and order descending. And then you could also limit how many of those you return if there are multiple matches. Okay. Any questions on all the keywords that we've encountered so far? They're pretty like, I would say it follows the intuition of what you're thinking, what you're saying, and then what you're actually putting on the page. So if it looks like it makes sense and you run it, it probably is right. before we move on, there's also one more thing I'd like to note. Notice that this semicolon is at the very end. There is no semicolon in between these lines. In a very C way, your command needs to end with the semicolon. You don't need to indent at all. We just worked with Python where indentation matters a lot. You technically could write all of this in one line, and it also still works if it makes more sense to you. And then I'll also show some example later where it might make more intuitive sense to keep things in like similar line. Like for me, if I was to run this query, for example, I would be like, select star from songs, where? And then I would start the next line, tempo is greater than 100, order by tempo, limit 1. It just splits out the logic to whichever way that makes the most sense to you. As long as like the information is there, you can move the lines however you would like. As long as it starts with your select and then it ends with the semicolon. Everything in between, it doesn't matter which line it is on. Okay, let's talk a little bit about aggregating, which is our last thing on here. So we have select count star from songs where tempo is greater than 100. Okay, we've seen these bottom two lines before. That's fine. Now we have this count star. Intuitively, without knowing any documentation, what do you think count returns? Yeah.
The number of something?
The number of something. Yeah. In this case, it's star, and then star, when we saw it earlier, select star, it just essentially is like a placeholder for every item. So like all of the attributes or all of the items in the column or something like that. In this case, select count, it's just going to count how many entries there are. So it's just going to return you like how many items in the database, basically. That matches this description. So all the lines work together. Okay, another thing. Select AVG, tempo, from songs. And while looking at it, and if you've ever like used Excel or anything, you realize that AVG stands for average. And so it's just going to give you the average tempo. Here are some aggregation keywords. So we just said average just now. We just took a look at count. Then we have distinct. Okay, distinct essentially just skips all the duplicates and return just like one time that it happens. The only like unique entries. There's also a unique keyword, but distinct like works with that. I mentioned earlier that we don't want duplicate pieces of information to exist between data tables. Why would there be a need for distinct here if we already made sure that that doesn't happen? Like, in what case does the same number can appear in multiple entries without it being duplicate information? Can you think of a scenario? I still think about songs. I have 5 songs, and for some reason, like a number appears like across them, but they're still unique values. Why is that?
They all have the same tempo.
They could all have the same tempo, right? And then similarly, same duration, same release year. Release year probably like happens a lot, but yeah. So distinct becomes helpful then, even though you made sure that like all the information is like unique. It doesn't repeat. It doesn't get sort of like redundantly placed anywhere. There are still going to be matching information across your database, and something like distinct allows you to get a clearer picture of the database itself rather than individual entries. So that might help with like looking at trends eventually in your pset when you're working on 50vil, looking at people, but we'll talk about that. And then also there's the intersect keyword. This doesn't get used very often in your pset. But as it says, it returns only results that are common to query 1 and query 2. Knowing that, you can probably also come up with like an alternative of how like the intersect keyword came to be by just like a series of select where like these matching criteria happen. It's just a shortcut essentially for the first and the second. So don't have to worry about this one too much. But if you do find a case for it, feel free to use it. But these top three are usually the ones that you would encounter. Okay, that is like the core material for today. Does anybody have any questions about the things that we have covered thus far today? I'm just going to recap them very quickly. Wow, gave me a stroke right. Okay. So we talked about sort of like the general design principles. You want things in one place, and then you want each table to be coherent. You don't want things repeating. And then we talked about the way that how to create tables, how to populate like these different pieces of information, the name, the primary key, and then the specification. We also looked at insert and update and delete. So just very basic functions that you would use to interact with the table. Then we have select star, and then a combination of these things. And then once we start looking at songs, we also looked at the four like big way to interact with data. So we have the selecting here with criteria, focusing on individual pieces of information. We have the like keyword to look at partial matches. And then we have the order by, which order by descending or order by ascending. And then ascending is by default if you don't specify. You also have limiting, limit by 1, limit by 5. You'll practice with these in the songs part of the pset, which we will take a look at right after this. So those are your keywords. When looking at aggregating, we looked at count to return the amount of entries. We looked at average, and then also distinct. Intersect, you can find alternatives for that, but if you would like to use it, feel free to do so. However, I don't think you need intersect that much. All right. Any questions on any of those? Any examples you would like to see before we move on? Yeah.
Can we go back to the database design slide first?
Yes, database design. So towards the start. This one.
Yeah. So when we're doing like a single entity, do we want to put like courses in their ID, people in their ID, students in their ID, all in separate things, and then match those? So it's just like 2 columns basically? Okay.
Yeah, similar to that. Yeah, exactly what you said. You want the different pieces of information to like exist in one table if possible. Like obviously, if you want to only make one table, you could put everything into there. The cost of that is every time you're trying to find a specific piece of information, you have to load the entire table. If you want to do any sort of aggregating, you have to go through all the entries. And so by limiting them in like these pieces, it's easier to just go through. Another thing is that while the code is running, if you remember limit by, which we just talked about, you can create an instance of the table where it's like a much smaller table that you're working with, and just a subset of the information. That way, if you like query through something with that, it will allow you to use less of the information than like to use everything at once. But in order to do that, you need to like have distinct areas. That way, like these categories, you can just use subsets of them rather than use all of them all the time. Yeah. All right. So that being said, we're going to move to our next thing, which is songs. All right. So for your pset this week, among the other things that you'll have to do, one of the lab items is songs. There are 8 files, which sounds like a lot, but they are very quick to work with. They essentially utilize everything that we've just talked about in this first half of the section. Some of the queries are much more intuitive than others. When you're working through them, I don't think any of them takes more than 6 keywords in order to get any of the queries. So if you're working through and you're like I'm lost, try to figure out what you're doing in like just like English words and then try to convert those into SQL terms. But in preparation for those, some abstract ideas that you might find helpful, just working on the songs, is how might we reference data across tables? Recall that just now we were talking about how like each table should have like a piece of information that's like unique to that table. That way you can use a subset of the entire database rather than like load everything at once. How do we reference things across the different tables? Because like John mentioned earlier in, I think, right here, just in the design of this, that if you want to look at the artist name, you have to first go to this one and then figure out what song it is, and then like go to the artist ID and then link them together. There needs to be this like linking part in order for the tables to make sense with each other. And so that missing link between the two tables is satisfied by the select and join keywords. And using a combination of these, you're able to create instances of the tables that connect your different pieces of information that weren't necessarily in the same table before. So let's just first talk about select. So in here, notice that artist ID in the first table matches with the primary ID in the second table, right? When we're talking about primary ID, we have like here in songs that they're just going through in the ID. The artist ID is what you're going to use to link these two tables together. They are the same entries in between. And important thing to note is that if the artist ID column did not exist, this table would make no sense. Because there is no sort of like linking factor, the piece of information that connects the two tables. You can only understand the tables one at a time because they have identifying features. And you need them both to be like correctly located and then also like there in your table. So just keep track of how you're linking the tables together, as that is very important when it comes to selects and also joins. Okay, so suppose we have this database with the songs and artist table. And our job is to query for all the songs by the artist named Oh Wonder. Okay. So intuitively, what is the right answer actually? So we're looking for all the songs that are written by Oh Wonder. Oh, sorry.
I think you'd use join on artist ID and ID, and then you'd want to select a song name from that table where artist is a wonder, or where name is a wonder.
Yeah. Perfect. Yeah. So essentially, if I'm a very visual learner, so if this makes sense to you, awesome. If it doesn't, I will try to find another way to explain it. If you essentially just take this bottom table by that column and you just move this onto there, that way it becomes two really long rows. That's what happens when like you're using joins and selects to combine tables. At these IDs, this column and that column are just going to merge like right there, and then you're going to extend this table with the content of here. And then at that point, you have two giant columns that's two giant rows that start up here and then continues here. So you can just look for the row that has Oh Wonder for a name, and then return the song name that is associated with that. Okay, that is like the abstract idea. How do we put that into actual like SQL terms? So we're trying to select the name of the song from the songs table that has the artist ID, whose ID matches up with someone else in the artist table with the name Oh Wonder. That is like, in one sentence, what we're doing. When we break it down into SQL terms, here's your first half, here's your bottom half. So again, like like this makes sense when you already see it, but like how do we like come up with it? So let's just break it down first. So select star. What does select star do again? As opposed to like select name or like select tempo. What's unique about star, essentially? Like what is star signifying here?
The entire row.
It's the entire row. Yes. So we're getting the entire row from songs, so the first table, where the artist ID is equal. And then suddenly we have this whole blob. Okay. This is very PEMDAS looking kind of like logic, where anything inside these parentheses, you'll just evaluate in here first, and then like you then evaluate everything outside. So let's take a look in here first. Select ID from artist where name is equal to O Wonder. So essentially, we're going to just look at all the IDs from the artist table and then return the ID of whichever row has the name O Wonder. When we do that, and focusing on just that part, we'll realize that, oh, we go to the artist table, we looked at the ID and has the matching name O Wonder. That entire expression inside of the parenthesis evaluates to 45. That is what gets returned because we just did select ID. So the ID gets returned. And then abstractly, this is what happens to the code. Everything that's inside there resolved to 45. And now your query becomes select star from songs where artist ID is equal to 45. Your original goal is to select songs from O Wonder. The idea of a song being from O Wonder simplified in computer terms to artist ID equals 45. And then so you get this query where it's just select star from songs where artist ID is equal to 45. Now, of course, when you're headed in to this database and you're working with it, you have no idea who's like what O Wonder's artist ID is. So you will have to write this like original query, right? And so the query itself is broken down to two parts, where the top part is what you're trying to do. And then the second part is whatever piece of information that you don't know that you have to join tables in order to figure out. In this case, that is artist ID, because by proxy, it represents the artist name, which is what you specified here. That's how we come up with most of the SQL queries that have to do with items in between different tables, is that we identify which column it is that they share. In this case, the artist ID column and so artist ID from songs matches up with ID from artists. They're very similar words. I am sorry that is just the way we came up with these tables. You can always come up with like other better ways to name these. But essentially, we realized that ID from artists and artist ID from songs are the key column that matches up. So we just use the select statement in order to link them together, resolve the second half in order to turn like the criteria of having a song by O Wonder to be equal to 45, and then resolve the original query, which lands you at this row. And because you did select star, the entire row gets returned, and then voila, you found the song and all its related information. Okay. Now, if you want to query for songs by artists born after 1980, again, looking at this, now we're targeting artists after 1980. So we're looking at birth year of artists in a very similar manner. We come up with something like this, where you're still selecting star from songs. And so now that part is like the same. Select ID from artist, that part's the same. Criteria changes, right? Birth year is now greater than 1980 because your query is different. Another different thing that I would like to note is that previously we did where artist ID is equal to blah, 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 blah. Now we have where artist ID is in blah, 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 blah. When we did artist ID equals, how many answers did we get? Like how many answers like resolve from like this query? It's only one. And that's why we did like artist ID equals. which is fine in that case. In this case, however, because it's not an equal sign, like the comparison you're doing here is greater than, there can be more than one outcome. You would use in as it might return like more than one item. Could you use in the case that there is one item? Yes. So usually to be safe, you could use in, but you could also, again, by security purposes, as we've mentioned at the very start of section, if you can be specific, if you know it's only one answer that will be returned, you can use the equal sign. But they're just very like nitpicky small details. If you want it to be general, just use in. It's generally pretty safe. Okay, so again, this inside resolves, and then we'll see, aha, it's 23 and 45 because both of these artists are born after 1980. So then 2 items gets returned into this list. And then now the top query just becomes both of these artists, which we went from here to linking to these items and then returning both of the rows that contain artist ID 23 and 45, which happens to be also both of them. Okay, so the distinction that we just made, in or equals. So you use in instead of equals when you're checking if something is in a list rather than just equal to a single value. So that's the difference between multiple, returning multiple items versus returning only one. Perfect match versus like one of like multiple choices. Okay, so that was select. And then we have a different keyword called join. And this join keyword, I have a love-hate relationship with joins. I think it's cool. I think it's intuitive. 9 out of 10 times when I'm writing SQL, I would always use selects and not joins. Because join, as opposed to select, join actually like in the computer combines the tables into this like new table essentially. Whereas select only temporarily take a look at things. Select, as a result, you can work with a subset of the information of the whole table, whereas join will look at all the items that matches up, which is just very costly and inefficient. But sometimes it is much more intuitive to just use join instead of select. So again, we have the same example of songs. If we were to join them together by the artist ID column, you'll just get this really long elongated table where there exists in this case, 2 columns that share the same information now, but they are the linking point of your entire database. Just gonna go back and forth between these two. Is there any question on how we went from 2 mini table to 1 large table in the same database? This is the difference between select and join. This is only 2 items in this example, but you could imagine like 50 items, thousands items, tens of thousands of items. And every time you use joins, all of them, like compounded by however many columns of attributes they are, every time you use join, it's just this huge, costly operation. But sometimes it's necessary. Okay. And how would you use joins? Similarly, you would do select star from songs, blah, 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 blah. But here, you would have join artists on songs.artistid is equal to artist.id. Okay, a little confusing of a line, but notice that we have artist underscore ID and ID. They are the attributes. Artist underscore ID refers to this column. ID refers to this column. But to the computer, there are still 2 separate tables before the join executes. So you have to specify that the left one is actually from the songs table and the right one is from the artists table. You technically could be extremely explicit and do that all the time for every single variable that you come up with. You don't have to, because sometimes there's only one case. But especially on songs, or, I'm sorry, not on songs, on joins and on any piece of information where you're working with potentially similar names across tables, it's usually a pretty good idea to explicitly specify which table it comes from, just so that you don't accidentally write something thinking like it solved the problem, but then the computer interprets it some way entirely different. But yeah, so you would join, and then specifically The dot notation here, right? This is the column. This is the table. ID is the column. Artist is the table. Very similar syntax to the way that we were working with structs when we were looking at the attributes inside of the struct, where it could be like candidate.name or candidate.vote, something from like week 4 that we were working on in the voting systems. Okay. So these top 4 lines essentially join the tables together. It creates this mega table. And now we were trying to do the query as we did on the very start when we were looking for songs by Oh Wonder. We just look at this table. Now we don't have to like move from table to table, reference this and that. We just have this giant table. We just go straight to name, see Oh Wonder, return that row. So the query becomes all 4 of this to figure out like how to combine the table. And then it just says where artist.name equals Oh Wonder. And then we're returning star, so that entire row gets returned. That's all the information that you would need actually to do pretty much the entirety of songs. So song 1, 2, 3, 4, 5, 6, 7, 8 is covered by that. For the most part, that is the introduction to SQL of this week. For the other items that you would have to do, I believe there's movies, which pretty similar to songs, but you'll just have to approach it slightly differently. Very similar concepts. Anything that we discussed in section today would be able to help you to figure out how to do movies. The big part of this week's PSET is 50ville. If you haven't looked at it already, just open it up. It's a really cool PSET. It's actually my favorite PSET. Yes, it is my favorite PSET. 50ville, just a very brief abstract about it. There is essentially a burglary. Oh no, MIT took the duck. Oh no. And your job is to figure out who committed the crime. And then you're given this database file, which you can go through, take a look at all the items, and then like using, say, flight times, transaction accounts, interviews, things like that. Just operating and working, figuring out how to like view information inside these tables. You're going to be able to piece them together and figure out essentially who like was committing a crime. Were there any suspects? Did they have any loss? Where did they go? You'll uncover a bunch of those as you go along. That is going to be the biggest chunk of this week's PSET. So have fun with that. Just to put it on your radar, the exam is the following week. We will that section next week is going to be a review section. So no new material will be given out, but we will essentially cover all of the abstract like main topics that we have learned thus far, and then also have some practice problems to go through in that section. So if you want review, show up next week to that one. And that being said, as always, we will have office hours throughout the week, and also the mega office hour on Sunday afternoon. PSAT is due April 5th. Oh, that says 5th, but 5th. And then as always, you can always email us to check in if you have any questions. So thank you all so much for coming to section 7.
Let's go to Mather's Day. It's sushi at 6.
Oh, it's at 6, right?
Yeah, so
Can we also, wait, you Shake Shack.
I go to Mather's.
Wait, can we go to Mother Sushi at 6?
Yeah, well, I will but essentially,
Can we get to Shake Shack in 3 seconds? And then we can start from that.
there will be
Or
you won't have access to it. Yeah, it's just like confidential.
So to
Oh yeah.
and then I just
We love
I've got me like here. This is what I'm doing. And then
don't forget to send your ID.
Is it on Canvas?
It would just be like
Canvas.
the actual.
Should be like an assignment on Canvas.
yeah, this.
You can just type. Or you guys can just type your ID into the spreadsheet.
Yeah. So
I guess I just like I was curious
It's more concept based. We will not have access to
function is carried out here. I just don't know where what I should type in. Space.
I wrote them. It's
Okay, but I don't write it. Okay.
and nothing in there is. There won't be anything from everything.
Okay. That's what I assumed.
All of the items, some of them are similar.
Elliot is like the best house.
There are coding questions, but like smaller.
Yeah, he's gonna renovate his house.
So like, are the coding questions relative to like,
That's so good. Like, that's like blah, blah, blah.
God, I'm not smattered.
Yeah,
They will a lot. They will be a lot more like triples. I would say you don't have to rewatch all the lectures because it takes forever. But
Coming up the stairs.
like the release and also the section notes, we will go over everything.
so it's well focused more
Uh-huh. It's going to be one and one. Like what it looks like in C versus what it looks like in I.
Okay. It's like if you had to like split up, it's like just like this percentage of it, does that. Can you give me like a rough breakdown?
So I don't remember for the spring one. It's pretty similar to the fall.
How is it that? How is it called?
You recommend me or constant?
45% C, and then like 95% in Python.
Okay.
And then like
Why do they have it?
And my reaction was like, no. But then Elliot.
With like Georgia,
Like within these like 45 CC whatever, like is it like just purely code or like half more than half?
I don't think it's half, but it is a combination.
My hand.
General.
Your entire hand is.
For example, like
I'm saying every single.
All of the fingers. She got
She's like this.
We no did add.
Raves, like it would be like
And then we thought for like 5
maybe
minutes.
like imagine you're getting stuff.
Like, alright, what's your name? She was like, no, there's no way.
Also, like, we don't expect everyone.
Wait, but if you go,
If you're able to put the abstract,
Yeah, not cool.
even if you don't have time to write it.
we have an hour to speak.
So is more different like actually coding?
Oh, so we just roll.
Your code could run into an error when you run it in if we understand your project, right?
Yeah. Because some like people told me from last semester like you had to like write code in like a text box and
But then will we
like my last question is that like so you know how like usually have like these type of specific like commands and stuff?
Like string compare, for example.
No, I mean like How do I like explain this? Like, they have like their own like world.
I also want to go to pyramid.
I don't know how to explain. Wait, never mind. I
Do
don't
you have an example, yeah, or
I pull up like a piece of.
sure, sure.
Pizza. So some hard jockey. Like I wrote like. When does the shadow so I wrote, for instance, this. So the first one. Did I write what I wrote in here?
So you submit this one. Okay. So yeah, that's perfect.
Trader Joe's is a 24-minute goal.
8 of them.
No, it's like 5 minutes.
You could, I think if you upload the folder, each of the files will pop up.
Perfect.
Yeah. Like, just have the auto grader run, and it should like tell you everything set up. If you did like all of these.
And then should I write it like
Really somewhat specific
indented, or should I write it like?
That is,
Can I give like an example of
when
making
I
a
write
table
this,
for
I would write it in
called
one line because it just makes sense to me.
Okay, because that's how I write it down here.
And
Oh,
then
okay. Yeah,
that
got you,
kind of
got you.
is about how I would actually do it.
Gail, do you want to go to Trader Joe's with us?
No, rather.
Yeah, and it,
And then a table
Yeah,
for
see,
like.
it's more of like,
what is the next
so like, you can use whatever to give you.
Wait, never mind. Never mind. Question. Never mind. Question.
You good?
I thought it was my question.
Okay.
So even though it's indented on, if you don't do this, it's a nice straight line.
Yes, like that's the thing I said about like the semicolon. Of how like as long as like it exists before the semicolon, everything that's in between it is treated as a line. So regardless of whether or not you start a new line or like that's all one line, it makes zero difference.
Oh, just like
it's just
wait.
really reading it.
Or like which represents.
Okay, perfect.
Yeah, what?
Awesome,
Yeah,
thank
what
you.
time is?
Of course.
And then a separate table.
Okay, maybe
Personal finance, you told me.
Totally than 2 minutes.
Oh no, we're not doing the channel. We're doing
I haven't dyed my hair red. I don't know if I'm gonna do it anymore.
I didn't get quoted, so my hair's not
Quoted,
red.
so you're not
We
getting.
got lather, which is worse.
Honestly,
I would assume.
my condolences, I guess.
No! We're in the season.
Yeah, I was thinking maybe like pages.
Okay, you have the better.
I have a photo of him in a bunny suit on housing day.
I was in a funny suit.
Are you created a brown mixer?
I'm planting a brown mixer. That's why I was at
Oh,
board.
yes.
Yeah. You know, I planned the last 2 brown mixers, so that was on me. Like the fact that we have access to Cafe Cafe.
Is your friend coming, the one that did the...
Yes, yes. She is on. Yeah, she was their VP, and then now she's a general member.
Are you coming to the Lee's dinner before? You should.
I'm not invited because I'm not on board.
Wait, but you're planning it. Just text Elizabeth.
Just Elizabeth,
I'm gonna
like,
pull up.
Can you show me? I'll see. I don't know.
You should.
Yeah, because I'm technically not on board, guys. I retired, and then like they pulled me out of retirement to like go plan. And I'm like,
Wait, then you're on board.
Yeah, you're on board.
It's like being
Like
employed
one of
again. Like
Yeah.
if you're employed, then you're on board.
Well, then you're on board for this.
Yeah.
True.
So then,
true.
so you can come to the Lee's dinner.
Yeah, I booked like the next like 3 like HBA events. Like well, I'm not booking that night, but I'm booking like the citation ceremony.
Yeah.
I booked like Northeastern just now, and I'm booking
Oh my
like
God.
Cafe Cafe. Like they just make me a position.
Wait, yeah.
I could be like
Yeah.
good booker. Like
You're
that's
an
me.
honorary board.
Just tag. That's your title.
Just tag. That's what
Tag.
it is. Yeah. But you guys take care.
Bye.
Have a good
Thank
one.
you so much. Where's my phone? Yeah.
Do you want me to call you?
Have like another food that one is also gonna have a different dining hall associated with it. Yeah, this is one of the sort of the things that's tough about kind of designing your database.
And then if you wanted to like get the food at a specific meal or something, you would probably need like a separate table for like the day and a separate table for like.
Well,
food
that's
of the day or
an
something like that.
interesting one. So you're saying so the meal is just breakfast, lunch, dinner,
Yeah.
but like the food item. Okay, I see.
Yeah, like food items might be different based on the day and based on which D hall you're at.
Mhm.
So it's like dependent on more than one
Yeah.
variable.
Yeah. So like you could have a different a different like you could have like the like food itself be like a table for each type of food.
Oh, and then do
And
like
some information.
IDs
Yeah, they
for
have an
those.
ID. Yeah.
Oh,
yeah.
okay. And then this is when you kind of want to do in reverse of how you'd actually search for it.
Yeah.
Okay, that makes sense. Thank you.
Yeah, these types of databases you can see right here.
Yeah, the dev started asking me stuff, and I was like, I have no idea how to construct this.
4, 6.
Thank you.
I have a list of IDs. You have a list of IDs.
I probably have whoever you don't have.
Roster.
Take care.
See ya. See you, Ruby. So have you actually used SQL on an actual project?
I did. Oh my god, you want to see? I'm so proud of this demo. I took CS50, right? And then I did my project, which is it was fine. And then David actually liked it because I put 3D modeling stuff on there. And I was like,
wait,
yo,
you do
this
3D
is sick.
models?
Yeah, wait, no, I use an external app to record 3D modeling stuff, and then I turn them into .mov files, and then I have them displayed on the
Oh, is this gonna be like a Blender tutorial website?
low key. It was just a website geared towards
Yeah.
incoming students. Be like, hey guys, blah blah blah, welcome to Harvard. Here are your helpful links, blah blah blah, stuff like that.
That's
But then that's my project. But this one,
because I'm gonna be honest, I have worked with multiple different databases, never SQL. Firebase and all that.
yeah,
So it's just a different type of database, but it has Python bindings. It's pretty cool though.
what was I doing? Oh, I was gonna show you this.
Yeah.
Python, and I literally still use this because this is my personal app. So
Oh, that's cool.
So yeah, this is it. Low key, it looks like a ton of stuff, but this is just this is literally 2 weeks from now. That's what they're learning.
Yeah.
And then style CSS, which is
There's a
dangerously long
Flask
conversation.
app.
Yeah, just a Flask app. But this is what I made, and it's just my contact page,
shit.
blah blah blah. Bro, I'm so proud of this. This is so lit.
It looks sexy.
And then you can create stuff, or you can go explore. And I made these song entries,
Whoa.
which it's basically you ever play guitar or whatever, and you look up the chords.
Yeah.
So I made these, and I also made the scrolling on the page too, because you have to pay money to do that. Or if you're on a normal on the normal guitar app, if you want to transpose something, you also have to pay for the premium subscription. Bro, I just make my own and be like,
Dude,
alright,
you
call it
popped
a day.
off.
This is I'm so proud of this. I still use this.
Holy shit.
I'd be in my dorm and be like, all right, time to make up a new song.
Yeah, dude, added something new to the database.
Right now.
Oh, that's sick. That's so cool. So, because you could do karaoke.
Exactly.
Yeah.
Yeah. I literally just added this song yesterday.
Whoa.
Yeah. And then single column, I made it centered, and I just scroll and I have my guitar and I just follow along.
Oh my gosh.
I want to change keys. I just boom, 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 boom.
Dude, that's sick.
I
So was your final project for this course, or was this after?
This is after. This is what else can I do? And then of course it's just running in the background. Just close it.
That's sweet. Yeah.
My actual project with this course is a third of the amount of information I have in here, and I did it in 2 weeks. But yeah.
Damn.
It's just a ton of CSS, so it looks cool, but
Yeah.
it's not complicated.
No,
It's
I
just a bunch
know
of
those animations are tough.
yeah. I legit I wrote the CSS file 3 times because it was just I started writing something and then I tried to overwrite it, but then I wrote the same exact thing and I just named it something differently.
Yeah.
I had to go back and all right, have to the amount of times in which I had to go back and
put them in actual sections
Yeah.
to like understand what I'm writing. Like it's lit.
That's awesome.
And there's all of this, which like low-key I had to look up to do some of this because I low-key was like, how do I connect this to Spotify?
Yeah.
Because like when you make a song and like, because in there right now, each of the songs has like a cover image, but like, I don't know how to like get a cover image and just put there like immediately.
Yeah.
So then I had to look like on how to like connect the Spotify API with it, so that every time I create a song, it like
So you're making the API
queries
call.
up.
I see it.
Yeah.
Does the Spotify API, does that have like a specific API key or is it just like public?
Yes, you can register one for free. It's like a
okay.
developer API,
Yeah.
and it just gives you like.
So it's
access.
probably happening on the back end.
Yeah. I was taking CS109, which is data science, and we need to do that for our project. I'm like, wait a minute, I can implement this for my own project.
Yeah. That's cool. APIs are fun.
Oh yeah.
I have one that is sketchy, but I want to say it after.
That way, is the recording still on? It's totally on, right?